Hi guys, this is Steph, and my problem was number 5. So let A be an element of G with the order of A equaling n, which has to be less than infinity. Prove that A to the I equals A to the J if and only if n divides I minus J. So we know since it says if and only if, we're going to have to prove it in both directions. Right there. So first we're going to prove it from left to right, so in this direction. So let the order of A equal n. So that means that A to the n must equal E, the identity. Also, let A to the I equal A to the J. So then I multiplied times A to the J inverse on both sides, on the right, and you get AI, A to the negative J equals AJ, A to the negative J. But, so these two, they just equal E. And I combined those two to get A to the I minus J equals E. So, there exists a Q and an R as a member of the integers, such that I minus J equals NQ plus R, where 0 less than or equal to R less than N. So basically that's just saying whatever number I minus J is, it's going to be N times some integer plus the remainder. So it's just turning into I minus J into like an expression with N in it, basically. So if R is 0, that means that N times an integer equals I minus J, which is what we want to prove. So we're going to keep going. So that would mean that A to the I minus J equals A to the NQ plus R. So I broke down the right side. A to the NQ plus R equals A to the NQ times A to the R. A to the NQ, you can just rewrite it like A to the N to the Q times A to the R. But we know that A to the N equals E from up there, so I replaced A to the N with E. So E to the Q times A to the R. E to the anything is just E times A to the R, and E times anything is just that thing, so we know it's A to the R. So now we know that A to the I minus J equals A to the R. We also know that A to the I minus J equals E. So if both of those things are true, that must mean that A to the R is equal to E. So now, we also know that R is in between, R is greater than or equal to 0 and less than N. So it's any number in between 0 and N. We also know that it has to equal 0 because if A to the R equals E, the smallest thing that makes A to the anything equal to E, the smallest element would be N. But we know that R can't be N. It has to be strictly less than. So what's the only other thing that would make something equal the identity? Would be the 0 power. So that's how we get R must equal 0. So that tells us that A to the I minus J equals A to the NQ plus 0. So A to the I minus J equals A to the NQ. So then we can say, oh, well, I minus J must equal NQ. So that means that A to the I minus J divided by N must equal Q, which would be an integer. So since Q is an integer, that means that N divides I minus J. So we proved it in one direction. Now we have to prove it in the other direction. So let the order of A be N, which implies that A to the N equals E, and let N divide I minus J. So, since N divides I minus J, we can say that there's some K as a member of the integers, such that N times K must equal I minus J. So, then we can say, well, if that's true, A to the NK must equal A to the I minus J. So, we just change A to the NK is the same thing as writing A to the N to the K. And then I broke down the I minus J. So it's A to the I, A to the negative J, or A to the J inverse. So we know that a to the n equals e from up here, so I replaced a to the n with e to the k. So e to the anything is just e. So e must equal a to the I, a to the negative j. Then I multiplied by a to the j on the right hand side, on both sides of the equality. These two cancel out, so I end up with a to the j equals a to the I. So we proved it in both directions, which means that a to the I equals a to the j if and only if n divides I minus j. That's it. Hope that made sense.